All right, good morning, honors chemistry. This is your honors lesson on resonance structure and formal charge. So we have just discussed Lewis diagrams, and I obviously am making this a little bit early, but basically we've discussed a way or a model, a visualization of how we can determine exactly how covalent bonding molecules share their electrons, how they distribute their valence electrons in order that a compound's individual atoms all attain or have access to an octet or a duet. And then, of course, we have some special ones that can do more than that, and some special elements that can do less than that. But the idea is that Lewis diagrams give us a more complete picture of how bonding occurs between atoms, specifically covalent bonding, the sharing of electrons. So now I want to introduce to you, and this is totally an AP topic, another feature of Lewis structures, an upgrade through resonance structure and formal charge. So when you follow my Lewis structure rules in order, okay, and you pay attention to all the little mini exceptions that you have, you can realize pretty quickly when you do enough Lewis structures of enough molecules that there are many types of valid Lewis structures that can be developed out of following those rules. So we call that resonance. Resonance occurs when various valid Lewis structures are true for a molecule. Okay, where various valid Lewis structures are true for a molecule. And of course, I'm going to add the emphasis following the rules of drawing Lewis structures, right? So for example, let's look at ozone. Ozone is O3, okay? What we say is that ozone has 3 oxygens, okay? And theoretically, what these oxygens here, these terminal oxygens, are what we call equivalent. They're the same element. They have the same level of reactivity. The question is, are they on the right or the left? And so resonance would tell us that there are 2 valid Lewis structures that we could draw following the rules. And you could determine that the double bond goes on the left and the double bond goes to the right, oxygen, terminal oxygen. And what resonance tell us is that the actual Lewis structure, that we see is an average of these valid Lewis structures. Okay, so what we see is that the actual structure of a molecule is really the average of all valid Lewis structures. If you're in your mind thinking, wow, this sounds familiar, this like concept of the actual thing is really an average or a combination, you're absolutely right. This should bring back feelings of isotopes, that there are various forms of something, of some type of matter, and that the actual matter is described as kind of an average or a combination of all of it, of all the various individual forms, right? So it almost has a similar concept as isotopes. Like obviously different application, right? Here we're talking about the actual structure, not the mass, but you're seeing kind of a pattern of thinking that we observe in chemistry. So when to check for resonance? When do you start looking at like, hey, maybe there's there's multiple Lewis structures that could apply to this, okay, and that I need to take account for when I'm determining the most likely structure, right? First is when you have the same terminal atoms, right? When that can double bond, that can double or triple bond. So like you don't really have to worry about halides, right? So don't worry about hydrogen or halogens because they can't double bond. They are always terminal atoms for the most part, but they can't double bond. So you don't have to worry if you have like NH3, like there's no resonance, like it's just single bonded. Resonance occurs when you have the same terminal atoms that can double or triple bond. Okay. Another type of situation where you might want to check for resonance is when you have a double or a triple bond at all. So here, what I'm saying is, okay, if you don't know, if it's not obvious that like, oh, look, I have all oxygens on the end, or oh, look, I have like all, what's another one that can double bond? Oxygen is really common exterior. It's really, really, really common. Oh, look, I have a bunch of like phosphorus or nitrogens, right? If you don't have all the same terminal atoms, but you do see a double or triple bond present in general, you might want to check if there was, following the rules, another way that you could have redistributed those electrons. Okay. So the big clue is same terminal atoms and double or triple bond is kind of the big idea. So let's look at an example. Let's do the nitrate ion, NO3, 1 minus. And what you would have realized is we should have done enough practice with Lewis structures by now. So I'm just going to draw the element. You would have gotten something like this. Oxygen, right? And actually, I'm going to draw it this way. So it looks, it's just kind of convention to draw it this way. Okay, you should have gotten something like this, I believe. And of course, you have your brackets and your charge on the outside. What we would say is, notice I have equivalent terminal atoms. They're all oxygen. That means they all behave the same chemically. So what I would say is, well, following the Lewis structure rules, I could have, and this is the symbol for resonance, a double-sided arrow, a single line double-sided arrow. I could have had another resonance form, another version, where instead of my double bond being on the top oxygen, my double bond is on the right oxygen. Okay. Or again, right? Maybe instead I say resonance structure, I could have moved my double bond resonance. Instead of being on the right, I could have put it on the left. Notice all of them are easily determined by the Lewis structure rules when you follow it in order. Okay, so this is kind of what we see. Go ahead and try sulfur dioxide on your own. It's a very similar concept. Try drawing its Lewis structure, the first one that you identify according to the rules, and then notice that you have all the same oxygens, okay, on the terminal atoms. And so try moving around whatever double or triple bond that you observe. So go ahead and pause me and do that on your own. All right, so hopefully you paused me and got these following 3 resonance structures, okay? So that hopefully feels pretty good. Not every single Lewis structure is going to be this easy. Remember, you could also just simply check because you have a double or present bond or triple bond present doesn't mean that all of the atoms have to be the same terminal atoms, right? But they're the easiest. They're like a pretty dead giveaway when you do see this. Like it's almost a guarantee that there's resonance when you do see this. But let's look at when you have more complicated, okay, Lewis structures that are all technically valid. How do you determine which one's the most dominant? Kind of like isotopes. How do you determine which isotope is going to be the most abundant version, the most dominant version, right? The most likely version, okay? And this is where formal charge come into place. Formal charge is once you've identified various resonance structures, various Lewis structures that are technically valid, what we do is we assign this charge, which is totally a fake charge. It's totally fake, okay? A fake charge used to determine the most likely valid Lewis structure, or another way of putting it is valid resonance, right? The most valid resonance structure, okay? So the way that we describe it is our equation says that our formal charge Fc is equal to the original amount of valence electrons minus the sum of the dots plus the lines. around a specific atom, okay? And so we assign, by the way, formal charge assigned to individual atoms in a molecule, okay? So before I show you an example, let me just kind of tell you some rules of how we like to assign these, okay? Other than just the equation, there's some other rules, some other preferences that we like. First and foremost, the most electronegative element always has the negative, okay? Always carries the negative formal charge. So if you have to have a negative formal charge assigned through your little mini equation here, you would prefer it be on the most electronegative element. That's one giveaway for the preferred Lewis structure. The second is that the formal charges of each atom is the closest to zero. We want to keep it low, like coefficients, right? We don't want you to write like 24,000 of this molecule and 60,000 of the next if you can simplify it to the lowest common value, right? So we want everything close to zero as possible. We don't want to be assigning charges upwards of even 3. Like pretty much we keep everything at like 3 and below, the closest to zero that we can. 3, the sum of the formal charges all have to add up to 0, or the sum of the charge of the molecule, or what was I trying to say? Or equal to the charge of I'm going to put equal to the charge of the charge molecule. So the idea here is that to be consistent, right? If you have a neutral molecule, you want it to 0. And if you, of course, you have like a polyatomic molecule with a charge, okay, you want your sum total formal charges to be equal to that same charge when added up. Generally speaking, the further you go down the list, the more important or the more prioritized. So let's look at an example, okay? Carbon dioxide actually has various Lewis structures, okay? We all know that through common sense that this Lewis structure is what we draw carbon dioxide as, okay? But let's say, following Lewis structure rules, somehow you gather the following. Instead, you do resonance right? You know, technically, that would be according to the Lewis structure rules, right? And so let's check this out for a second and let's say to ourselves, okay, why doesn't this work? All right. Everybody has an octet. I've used up all my electrons. Why do we say that this one is a no, but this one is a yes? Let's figure this out. So let's assign formal charges to each individual atom within it. So this oxygen, okay, right here, this oxygen going to have a formal charge of, well, how many valence electrons does oxygen originally bring? 6, minus the dots and the lines. So the dots are 1, 2, 3, 4, and 2 lines. So that equals 0. Oh, okay, that's actually nice. Okay, that's actually nice. We say 0 is formal charge for that atom. Let's go to carbon. Carbon comes in with originally 4 valence electrons, and it has no dots, but it does have 4 lines. Oh, that's also 0. So again, that's really nice. We like to keep it close to 0. Let's look at this other one. Okay, again, we would have 6 minus 4 plus 2, which is equal to 0. Okay, that's actually nice. Everything's 0. And if we add up our formal charges, 0 plus 0 plus 0, it does equal our overall charge of the molecule, which is neutral, 0. So now let's look at the other one. Okay, I'm going to change colors. So hold on, let me change it to purple. So this one minus dots let's start there. The valence electrons that oxygen brings is 6, minus the dots plus the lines is 6 dots and 1 line. So that equals -1. Okay, I'm okay with that because oxygen is pretty electronegative. It would make sense that if it's going to have a formal charge, a fake charge, that it would probably take on a negative fake charge because it's very electronegative. It hogs or attracts negative sources of electrons, right? Okay, I'm not the worst at that. It's not zero, which is preferable, right? The closer you can get to zero is better. But okay, let's try, oh, 1 second. Let's try carbon. So carbon, it comes with a formal charge of, let's see, valence electrons 4 minus dots plus lines, no dots, but still lines. Okay, 0. It also has a formal charge of 0. So, we're not looking too bad. Okay, what about this one? Let's go back to blue. This oxygen. Okay, this oxygen, original valence electrons is 6 minus dots plus lines. Well, 2 dots plus 3 lines, and we get equals to 5. Oh, sorry, plus 1. Wow, I cannot do math. Okay, so this is a plus 1. Okay, so here's a problem. Technically, the sum of the formal charges do add up to 0, right? -1 plus 1 plus 0 is 0. But here's where the rules come into place. One, I have two equivalent terminal atoms, oxygen, which are both electronegative, but one oxygen holds more electronegativity than the other. That doesn't make sense. That doesn't sound preferable. Kind of defies the chemical behavior of oxygen. And two, why would I choose a structure that gives me something above 0 when I can achieve what I want to achieve, octet rule, duet rule, and so forth, with a structure that keeps me at 0, both individual formal charge and some formal charge, right? So this is why this structure of carbon dioxide is considered the preferable one. It's because according to formal structure, we can determine that it's just more favorable. The very makeup of it is just more favorable. Maybe the end goal is kind of similar in terms of you achieve the octet rule and you achieve the duet rule and you used up all your shared valence electrons, but the actual way that the structure is built is just overall better, lower energy, the closer to 0, the better, follows all the rules and so forth. So this is how we use formal charge to determine which resonance structures are the most dominant or the most likely for a specific molecule. Okay, so here's another practice question, cyanate ion. I want you to try this one on your own. Hint, there's definitely a double or multiple bond of some sort. Notice that you do have an overall -1 charge. So your Lewis structure should have a bracket around it, and you should add an extra electron to your total valence electron count. And two, your formal charge here is now going to add up to -1. Okay, so go ahead and give this a try and pause me and then resume me when you're ready to check your answer. All right, so hopefully you got the following, maybe not in the same order in terms of which Lewis structure and resonance you identified first, but hopefully you got these 3 resonance structures. Okay, notice double, triple bond is present, right? So we could check for that. I do show you the formal charge above, and you should notice, of course, that each resonance does have a formal charge sum that totals to -1. So you do meet that criteria immediately. But what you'll notice is that, let's look at this one, okay? This one is an automatic no because you have nitrogen, you have really high formal charge values, right? You have up to -2. We want to get as close to 0 as possible. In addition, you have the least electronegative terminal atom, nitrogen versus oxygen. Nitrogen has less protons, therefore it has less Coulombic attraction, therefore it is less electronegative. You have that one carrying the negative charge out of the 2 terminal atoms. So that makes no sense. That's an automatic no. The next one is, okay, it's comparable to the other resonance, and it does add up to -1. Sum total of the formal charge does add up to the overall charge of the ion, right? But what we have here is that, again, your electronegative terminal atom, the more electronegative terminal atom, is oxygen, not nitrogen. So it just wouldn't make sense that nitrogen would carry a formal charge of the -1 if a formal charge of -1 has to be carried, which it does. So what you're left with is, this is the best option following the rules of Lewis structures and the preferable rules of identifying the best Lewis structure via formal charge. You have values as close to zero as possible, and you also have the negative formal charge on the most electronegative atom, okay, present. So this is why this would be the correct structure for the cyanate ion. I just want to mention one last thing. Notice how a small detail for you honors slash AP driven kids. Notice that when I write formal charge, okay, when I write formal charge, I write the sign and then the number. But when I write actual ion charge, right? Ion charge. Oof, gee willikers, that just got worse and worse. I write the number and then the sign. Now, I haven't been too good about this in the honors co-seated class because I don't want to stress out the prep kids. I just kind of let it be because that's how they think. That's not a priority for them, right? It doesn't matter. As long as they understand charge, that's all that matters. But you guys are being held at a higher level. You are learning more of the nuances of how we communicate in chemistry. And one of the biggest ways we communicate is the very notation of how we write things. So when I write formal charge and when you write formal charge, you communicate to me that this is a fake charge by putting the number after the sign, plus or minus, right? After the sign, plus or minus. But when you are talking to me about actual ion charge, not a fake charge, you do the number and then the sign. So it's a really small detail, but that's something that you want to keep in mind. Go ahead and try out your workbook problems. The answer key is available online through the website, and you guys will be quizzed on this on the Lewis structure quiz coming up in just a couple days. So best of luck. Contact me if you have any questions, but my biggest suggestion is just get in there and start practicing. The best way to learn these things is through repetition of doing. All right, guys, good luck. Bye.